Hello students, in this video we learn about Bessel differential equations. A differential equation of the form x square y double dash plus xy dash plus x square minus n square into y equal to 0 is called Bessel differential equation of order n, and its particular solution is called Bessel function of order n, where n is non-negative real constant. Now we shall find the series solution for Bessel differential equation. For that, consider the Bessel differential equation x square y double dash plus xy dash plus x square minus n square into y equal to 0. Call this as equation 1. Now we assume that y equal to x power k into a naught plus a1x plus a2x square plus a3x cube plus etc. up to infinity, or in summation form y equal to summation of ar x power k plus r from 0 to infinity be the series solution of equation 1, where very important a naught is not equal to 0. Now we will find what is y dash and what is y double dash. Now y dash is given by, here ar is constant, so we will write ar as it is. Derivative of x power k plus r is k plus r into x power k plus r minus 1. So y dash is summation of k plus r ar x power k plus r minus 1. Now similarly y double dash is, again ar is constant, k plus r is constant. Derivative of x power k plus r minus 1 is k plus r minus 1 into x power k plus r minus 2. Now we will substitute y dash, y double dash in equation 1. In equation 1, that is this equation, we get x square y double dash is summation of k plus r into k plus r minus 1 ar x power k plus r minus 2 plus xy dash, x we will write here, y dash is summation of r from 0 to infinity k plus r ar x power k plus r minus 1 plus x square minus n square into y, that is x square minus n square. Y is summation of ar x power k plus r, where r runs from 0 to infinity, is equal to 0. Now we will simplify these equations. I will take this x square here, x square into x power k plus r minus 2, it becomes x to the power of k plus r. So the first term becomes summation r from 0 to infinity k plus r minus 1 ar into x power k plus r, plus second term, you can observe here, x into x power k plus r minus 1 is nothing but x power k plus r. So that second term becomes summation of k plus r ar x power k plus r, plus the next term I will multiply x square into this term. So when you multiply, what you get is summation of r from 0 to infinity ar x power k plus r plus 2 minus n square, my summation of r from 0 to infinity ar x power k plus r is equal to 0. Now from first term, second term, and fourth term, you can observe that summation of r from 0 to infinity a r x power k plus r is common. A r x power k plus r is common. So I will take from first, second and fourth term summation of r from 0 to infinity a r x power k plus r as common. Then the common terms are k plus r into k plus r minus 1 plus k plus r minus n square. So by clubbing first term, second term and fourth term, what we get is summation r from 0 to infinity k plus r into k plus r minus 1 plus k plus r minus n square. These are common things, a r x power k plus r, and my third term plus summation of r from 0 to infinity a r x power k plus r plus 2 is equal to 0. That is, if I simplify here, k plus r is common, then it is summation r from 0 to infinity, k plus r is common, then the remaining term is k plus r minus 1. Already k plus r is taken out, so it is plus 1 minus n square. You have to put the brackets carefully. Multiplied by, all these things are multiplied by a r x power k plus r plus the next term summation r from 0 to infinity a r x power k plus r plus 2 equal to 0. Here minus 1 and plus 1 cancels. Here you can observe a power r x power k plus r in the first term summation. Second term we have x to the power k plus r plus 2. So what I do is I will replace r by r minus 2 in the second term, that is here, to make x power k plus r power x power k plus r as common. So if I replace r by r minus 2 in the second term, so what I get is summation of a r is replaced by r minus 2 x power k plus, if I replace r by r minus 2, then minus 2 and plus 2 cancels. What I get is x power k plus r. Now the first term is summation of r from 0 to infinity k plus r into k plus r, here k plus r whole square minus n square into a r x power k plus r plus summation of r from 2 to infinity a r minus 2 x power k plus r is equal to 0. Now students, you can observe the first summation starts from r equal to 0 and the second summation starts from r equal to 2. To make these two summation as common, what I do is I will expand the first summation. That is, when r is 0, this term becomes k square minus n square into a naught x power k plus, when r is equal to 1, this becomes k plus 1 whole square minus n square into a1 x power k plus 1 plus, for r equal to 2 to infinity, I will write the first term as like this, summation r from 2 to infinity k plus r whole square minus n square a r x power k plus r plus summation r from 2 to infinity a r minus 2 x power k plus r equal to 2 equal to 0. Sorry. Now I will write first two terms as it is, that is k square minus n square into a naught x power k plus k plus 1 whole square minus n square into a1 x power k plus 1 as it is. And from third and fourth term, you can observe summation r from 2 to infinity is common, x power k plus r x power k plus r is common. So I will take it as common, summation r from 2 to infinity x power k plus r. The rest of the terms are k plus r whole square minus n square plus ar minus 2. So it is equal to 0. Now equating the coefficient of x power k plus 1 and x power k plus r to 0, we get from the first term the coefficient of x power k is k square minus n square into a naught is 0. So this will imply either k square minus n square is 0 or a naught is 0. But initially we have assumed a naught is not equal to 0. So k square minus n square has to be equal to 0. So k square is n square, k is equal to plus or minus n. So k value what we have got is k equal to plus or minus n. Now k plus 1 whole square minus n square into a1 is equal to 0. This implies that k plus 1 whole square minus n square is 0 or a1 is equal to 0. Again this will imply that k plus 1 whole square is n square or a1 is equal to 0. K plus 1 is plus or minus n from this equation or a1 is 0. But k is equal to plus or minus n minus 1. From this, if I write the expression for k is plus or minus n minus 1, which is not possible because already we know that from previous step, that is here, k is plus or minus n. So k cannot be equal to plus or minus n minus 1. So we are left with only one option, that is a1 has to be 0. Now we will equate x power k plus r, coefficient of x power k plus r to 0. What we get is k plus r whole square minus n square into ar plus ar minus 2 is equal to 0. So from this, AR is equal to minus AR minus 2, if you take it to the other side, divided by k plus r whole square minus n square. We will call this as equation 2, and this equation 2 is valid from r equal to 2 to infinity, or we can write it as r greater than or equal to 2. Now, first case, when k is plus n, the equation when k is plus n, equation 2 implies ar becomes minus ar minus 2, k is replaced by n plus r whole square minus n square. So on simplification, this will give ar equal to minus ar minus 2 expand n plus r whole square, n square plus r square plus 2nr minus n square. So plus n square minus n square cancels. What we get is ar equal to minus ar minus 2 divided by r square plus 2nr. Call this as equation double star. This equation double star is valid for r equal to greater than or equal to 2 or r equal to 2 to infinity. So for r equal to 2, what we get, we will see what we get in equation double star. When r is 2, this becomes a2 is equal to 2 minus 2, 0, that is minus a naught divided by r square, 2 square is 4 plus r is 2, 4n. So it will be minus a naught, 4 is common here, 4 into 1 plus n. Now similarly for r equal to 3 in equation double star, what we get is a3 equal to minus a1 divided by r square, 3 square is 9 plus 2nr, r is 3, so 6n we get. But we know that a1 is 0, therefore a3 is also 0, because if a1 is 0 here, a3 is definitely 0. Now for r equal to 4 in equation double star, we get a4 equal to minus a2 divided by 16 plus 8n, that is minus a2 divided by 8 is common, then it is 2 plus n. But what is a2? a2 is minus a naught divided by 4 times 1 plus n. So we will substitute that a naught here. So what we get is a4 as equal to minus of minus becomes plus. So a naught divided by 8 into 4, 32, 2 plus n into 1 plus n. For r equal to 5, in equation double star, what we get is a5 equal to minus a3 divided by 25 plus 10n. But we know that from previous step a3 is 0. If a3 is 0, definitely a5 has to be 0. So a5 is 0 and so on. Now we will substitute this a0, a1, a2, a3, a4, a5 in equation star. So we get y equal to, we have already y equal to x power k into a0 plus a1x plus a2x square plus a3x cube etc. be the series solution of equation 1, we said already. So for first case k equal to n, I will denote the solution, my first solution as y1. So y1 equal to x power n, because k is n, a0 plus a1 is 0, a2 value is minus a0 by 4 times 1 plus n into x square plus a3 is 0 plus a4, a0 divided by 32 times 1 plus n into 2 plus n x power 4, a5 is 0 plus etc. So on simplification, you can observe a naught is common, so I will take it outside. So y1 equal to a naught x power n times, then the remaining terms are 1 minus, we can write x square by 4 as x by 2 whole square, 1 by 1 plus n, plus x power 4 by 32 can be written as x by 2 whole square into 1 by 2 times 1 plus n into 2 plus n plus etc. So similarly for k equal to minus n, we denote the solution as y2, and y2 is given by a0 into x power minus n is replaced by minus n, 1 minus x by 2 whole square, 1 by 1 minus n instead of plus n minus n, plus x by 2 whole square, x by 2 to the power 4, 1 by 2 to the 1 by 2 times 1 instead of 1 plus n, 1 minus n, 2 minus n plus etc. So therefore general solution of equation 1 is of the form y equal to a y1 plus b y2, where a and b are arbitrary constants. So we have to choose this a naught as 1 by 2 to the power n into gamma of n plus 1, and we denote the solution as y1. If we choose a naught as 1 by 2 to the power n gamma of n plus 1, and we denote the solution as y1, and the expression for y1 is given by, you have to remember this, I have not done the simplification part, y1 is given by summation of minus 1 to the power r divided by gamma of n plus r plus 1 into r factorial x by 2 to the power n plus 2r, where r runs from 0 to infinity. The above function, that is this one, is called Bessel function of first kind of order n and is denoted by Jn of x. This is most important. That is, Jn of x expression you should be able to remember. That is, Jn of x is given by summation of minus 1 to the power r divided by gamma of n plus r plus 1 into r factorial x by 2 to the power n plus 2r, where r runs from 0 to infinity. Similarly, for k equal to minus n, we get a Bessel function of first kind of order minus n. For k equal to n, we get first Bessel function of first kind of order n. For k equal to minus n, we get a Bessel function of first kind of order minus n and is denoted by j minus n of x, and this j minus n of x is given by, very easy, minus summation of minus 1 to the power r divided by gamma of, instead of n minus n plus r plus 1 into r factorial x by 2 to the power minus n plus 2r. So therefore the series solution for equation 1, by choosing a naught as 1 by 2 to the power n gamma of n plus 1, we get it as y equal to a into jn of x plus b into j minus n of x. So thus the series solution of Bessel function or Bessel equation is y equal to a into j n of x plus b into j minus n of x.